Okay, I will share my screen. Okay, okay, ma. So is my screen visible to you? Yeah. Okay. So, therapeutic equipment. Last time we have studied medical instrumentation, right? So, therapeutic equipment is like the continuation of what you studied in medical instrumentation. So, medical instrumentation, you have studied about the basics, right? So, what are the different signals, what are the different electrodes, sensors, and stuff like that. And in therapeutic equipment, you will be mainly studying with medical equipments which are used for treatment purpose. So, treatment in the sense therapeutic therapy, abdinale, it refers to the treatment. Okay, so here, this is just a quick summary of your therapeutic devices. So, either it is used to assist a patient or it is used to assist a medical personnel in delivering the therapeutic services. Okay, so that's what therapeutic devices are. So, patient assistive devices include hearing aids, visual aids, or any other device, and other devices include ventilators, incubators, anesthesia machines, heart lung machine, ECMO dialysis, and radiotherapy equipment. So, all these things we'll be studying in your subject. Okay, so if you look at the concept map of your subject, here you can see five different groups. First group is cardiac assist device. So cardiac assist device, like we know, cardiac refers to heart, right? So here we are going to assess the functioning of the heart. So for that we have two main devices. One is pacemaker, another one is defibrillator. So first unit deals with pacemaker and defibrillator. So these are the very important cardiac devices which are still in use. Okay, and second category is diathermy and medical stimulators. So diathermy and medical stimulators, these devices are mainly used for surgery purposes. So diathermy is one technique where you use heat to cut the tissues or to heal the tissues and to heal the wounds. Okay, so diathermy is one technique. And third unit deals with extracorporeal devices. Extracorporeal means you are going to place a device outside the body, but the device will be connected to the body. So here we have two different groups. One is hemodialysis, another one is heart lung machine. So hemodialysis, this equipment deals with the kidney function. So when the kidney is not functioning properly, this dialyzer will be connected to the patient and it will perform the action of the kidney. So it will purify the blood, it will remove all the waste materials from the blood and it will return the purified blood to the body. So that is hemodialysis. Second one is heart lung machine. So heart lung machine, it is mainly used during the cardiac surgery. When there is an open heart surgery, the rib cage will be cut and in that case the heart will be directly connected to the heart lung machine. So the blood will be taken from the body and the functioning of the heart and lung will be performed by that machine. So that's why it's called a heart lung machine. Okay, and fourth unit is about respiratory aids. So here we will see about ventilators and respiratory equipments and incubators. So all these things will be studying in your fourth unit. And the last unit is about radiation therapy and radiation safety. So radiation therapy, main one clinical application is your cancer treatment. So here we'll study what are the different techniques which are used and how we are going to measure the radiation and what are the different principles that we have to follow. Because when you are going to give some radiation to the body, it should not affect the other parts, right? So you are just going to cure the cancer. So we'll be studying all these things in your fifth unit. Okay, so these are the 5 units. So and this is the overview and this is the syllabus. And in lab equipments, we'll be lab experiments. We'll be studying about diathermy, pacemaker, spirometry, stimulator, diathermy and ECG simulator, syringe pump and infusion pump. Okay, so this will be seeing in your therapeutic equipment lab. So I have already shared this teams, right? So we have 4 members in a team, so 8 teams will be doing the lab experiments. Okay, and all other activities we'll be doing as a team only. Okay, yeah. So this is the syllabus. Now we'll move on to the introduction. So here I'll just play this video. Just give me a minute. Yeah, so this is just to recap your cardiac arrhythmias. So in your previous subject in medical instrumentation, you would have studied about ECG, normal ECG and abnormal ECG, right? So this is just a recap.
Cardiac arrhythmias can be classified by site of origin. Sinus rhythms originate from the sinoatrial node, or SA node. Atrial rhythms originate from the atria. Ventricular rhythms originate from the ventricles. Sinus rhythm is the normal rhythm of the heart set by its natural pacemaker in the SA node. In a healthy heart, the SA node fires 60 to 100 times per minute, resulting in the normal heart rate of 60 to 100 beats per minute. The most common variations of sinus rhythm include sinus bradycardia, when the SA node fires less than 60 times per minute, resulting in a slower heart rate of less than 60 beats per minute, and sinus tachycardia, when the SA node fires more than 100 times per minute, generating a faster heart rate of greater than 100 beats per minute. Sinus bradycardia and sinus tachycardia may be normal or clinical depending on the underlying cause. For example, sinus bradycardia is considered normal during sleep, and sinus tachycardia may be normal during physical exercises. Cardiac arrhythmias that originate from other parts of the atria are always clinical. The most common include atrial flutter, atrial fibrillation, and AV nodal reentrant tachycardia. These are forms of supraventricular tachycardia, or SVT. Atrial flutter, or A-flutter, is caused by an electrical impulse that travels around in a localized self-perpetuating loop, most commonly located in the right atrium. This is called a reentrant pathway. For each cycle around the loop, there is one contraction of the atria. The atrial rate is regular and rapid, between 250 and 400 beats per minute. Ventricular rate, or heart rate, however, is slower, thanks to the refractory properties of the AV node. The AV node blocks part of atrial impulses from reaching the ventricles. In this example, only 1 out of every 3 atrial impulses makes its way to the ventricles. The ventricular rate is therefore 3 times slower than the atrial rate. This is an example of a 3-to-1 heart block. Ventricular rate in A-flutter is usually regular, but it can also be irregular. On an ECG, atrial flutter is characterized by absence of normal P wave. Instead, flutter waves, or F waves, are present in sawtooth patterns. Atrial fibrillation is caused by multiple electrical impulses that are initiated randomly from many ectopic sites in and around the atria, commonly near the roots of pulmonary veins. These unsynchronized, chaotic electrical signals cause the atria to quiver or fibrillate rather than contract. The atrial rate during atrial fibrillation can be extremely high, but most of the electrical impulses do not pass through the AV node to the ventricles, again thanks to the refractory properties of the cells of the AV node. Those that do come through are irregular. Ventricular rate, or heart rate, is therefore irregular and can range from slow, less than 60, to rapid, more than 100 beats per minute. On an ECG, atrial fibrillation is characterized by absence of P waves and irregular narrow QRS complexes. The baseline may appear undulating or totally flat depending on the number of ectopic sites in the atria. In general, larger number of ectopic sites results in flatter baseline. AV nodal reentrant tachycardia, or AVNRT, is caused by a small reentrant pathway that involves directly the AV node. Every time the impulse passes through the AV node, it is transmitted down to the ventricles. The atrial rate and ventricular rate are therefore identical. Heart rate is regular and fast, ranging from 150 to 250 beats per minute. Ventricular rhythms are the most dangerous. In fact, they are called lethal rhythms. Ventricular tachycardia, or VTach, is most commonly caused by a single strong firing site or circuit in one of the ventricles. It usually occurs in people with structural heart problems such as scarring from a previous heart attack or abnormalities in heart muscles. Impulses starting in the ventricles produce ventricular premature beats that are regular and fast, ranging from 100 to 250 beats per minute. On an ECG, VTach is characterized by wide and bizarre-looking QRS complexes. P wave is absent. VTach may occur in short episodes of less than 30 seconds and cause no or few symptoms. Sustained VTAC lasting for more than 30 seconds requires immediate treatment to prevent cardiac arrest. Ventricular tachycardia may also progress into ventricular fibrillation. Ventricular fibrillation, or VFib, is caused by multiple weak ectopic sites in the ventricles. These unsynchronized, chaotic electrical signals cause the ventricles to quiver or fibrillate rather than contract. The heart pumps little or no blood. VFib can quickly lead to cardiac arrest. VFib ECG is characterized by irregular random waveforms of varying amplitude with no identifiable P wave, QRS complex, or T wave. Amplitude decreases with time from initial course VFib to fine VFib and ultimately to flatline.
Okay. Am I audible now? Yes.
Yes, ma'am.
Okay, great. Okay, so we saw the recap of the different fibrillation conditions, right? So atrial fibrillation, ventricular fibrillation, tachycardia, and bradycardia. All these things happen because the electrical impulses do not travel properly inside the heart. So that's the main reason. So pacing refers to speed. So the speed at which the electrical impulse travel through the heart. So when normally in your heart from SA node to AV node, the signal will be transmitted. From AV node, it will go to the Purkinje fibers and the ventricles will contract, right? So if that electrical conducting system is not working properly, if the SA node is not working properly, if the AV node is not working properly, or if the Purkinje fibers is not working properly, in that case, you will need an artificial pacemaker. So pacemaker means it's going to speed up the pace of the heart rhythm, right? So or it's going to make the heart rhythm normal. So normal pace or the normal speed of the heart rhythm will be maintained when you use an artificial pacemaker. So you all already know that SA node is the natural pacemaker, right? So when the natural pacemaker fails to maintain the normal rhythm, we go for an artificial pacemaker. Okay. So we all know this, right? Heart has an intrinsic pacemaker, so it generates electrical impulse that travel along the specialized conduction pathway. So this conduction process makes it possible to heart to pump the blood efficiently. So this is what happens during the conduction. An impulse begins at the SA node and it causes the atrium to contract. So when the SA node is transmitting the impulses, the atrium will contract, and when it reaches the AV node and through this Purkinje fibers, when it is reaching through the Purkinje fibers, the ventricles will contract, right? So this is the process. So here you have this bundle branches which go through the ventricles and thereby causing the contraction in the ventricles, right? So in the diseased heart, what happens is that there won't be any impulses which will be generated from the SA node. Whether this SA node will be not transmitting or there won't be any transmission from the SA node to AV node. So either of these things might happen. Either it is unable to generate the electrical impulses or it is unable to transmit. So in that case, the heart is not able to pump the blood properly. So we go for an artificial pacemaker. So when you go for an implantable pacemaker, implantable means you are going to place that equipment inside the human body. So whatever you are going to keep it inside, it's called an implant. Either it can be a dental implant or it can be a heart implant, kidney implant. Okay? So transplant is different, implant is different. Implant is you are going to keep a machine or a small equipment inside. Transplant is an organ. So kidney transplant or heart transplant is you are going to take a live organ from a deceased body or from a donor and you're going to keep it to the person. Okay, so that's the difference between implant and transplant. Okay, so when you're going to implant the pacemaker inside, it has two main components. Yes, is there a doubt?
Screen is not shared, ma'am.
Oh, I lost my network connection. Okay, let me check. Just give me a minute. There's some network issue. Okay, just give me a minute. Okay, let me share in my mobile because in system it has not it's not showing. Okay, I'm sharing my screen. Are you guys able to see my screen? Yes.
Yes, ma'am.
Okay, great. Okay, so this slide you would have seen, right? No, none of the slides were visible. Up to which slide did you see? Up to this?
The title slide only visible, ma'am.
Cherry. Okay, then I'll start from the beginning. Okay, so heart has an intrinsic pacemaker, right? So we know that. Uh, just a minute. They just close the mic. No. Okay. Okay. So it has an intrinsic pacemaker, which is a SA node. So from SA node, the signals will be transmitted to the AV node, and then through the Purkinje fibers, and then through the ventricles, the heart will pump the blood, right? So diseased heart. In diseased heart, what happens is the SA node is unable to generate the signals, or it is unable to transmit the signals from SA node to AV node. So here, when an implantable pacemaker, you are going to place it inside the body, it will have two main things. One is a lead wire, another one is implantable pulse generator. So the pulse generator is the main component of your pacemaker. So here you will be designing the circuit so that it is able to exactly replicate your heart rhythm, which is ECG waveform. So the exact PQRST waveform has to be generated from this pulse generator. And second main component is your lead wire. So this lead wire will transmit the signal to this heart. So this signal will be transmitted through the lead and it reaches the ventricles. So from here it reaches the Purkinje fibers and then the heart will start contracting. Okay, so this pulse generator and the lead wire are the two main components of your implantable pacemaker. Okay, so if you look at the parts here, you can see the lead and then implantable pulse generator, anode and a cathode. So it has two sets of electrodes. One is anode, another one is cathode. Anode is a positive electrode and cathode is the negative electrode. Okay, so this is a complete circuit for your pacemaker. So what happens inside the pulse generator is that it will contain a battery and then a circuit. So the battery, it has to have a long life because when you are going to keep a pacemaker inside the body, it has to at least keep the patient alive for at least a minimum of 10 years. You can't just take a pacemaker for every week and then do a surgery and then keep it inside, right? So the battery which is going to be kept inside the pacemaker has to have a long shelf life, okay, and it has to keep the patient alive by continuously supplying the power. Second one is the circuitry which controls the pacemaker operation. So this circuitry, depending on this circuitry, you will be classifying the pacemakers into different types, which we will be seeing in the next class. Okay. And the next component is lead. So lead is an insulated wire. So like how we have electrical wires in your home, right? So inside the wire, the current will be traveling, but the outside part of the wire will be insulated. So similarly, there will be insulated wire which will be used to deliver the electrical impulses from the pulse generator to the heart. So Yeah, that lead will have two functions. One is to deliver the electrical impulses, another one is to sense the cardiac depolarization. So this depolarization and repolarization you guys would have studied already in medical instrumentation, right? So depolarization is when there is a contraction, there will be a depolarization. So in that case, once the signal is sent, the muscles will contract, right? So how much level of contraction is occurring, this lead has to know. Only then the next pulse has to be transmitted. So for each pulse, there will be a contraction, right? So this timing of the pulse, the amplitude of the pulse, the frequency of the pulse, everything is important. So for that, you need to sense the cardiac depolarization. So whether the muscle is contracting or not, you should be able to identify it, right? So because you're going to keep that equipment inside, that equipment has to monitor the heart rate and also it has to maintain the heart rate, right? So this pacemaker has to perform these two functions. So we have a sensor inside. So types of leads. We said that lead is an insulated wire, right? So we have different types of leads. One is endocardial lead, another one is myocardial lead. So endocardial means you are going to keep it in the innermost layer of the heart. Myocardial is the middle layer of the heart. So in anatomy and physiology, you would have studied different layers of heart, right? So epicardium, myocardium, endocardium. So endocardial leads are the leads which are going to go inside the innermost layer of the heart. Myocardial is the middle muscular surface. Okay. So this is a transvenous lead that have a fixation mechanism. So this is a passive fixation. So when I say passive fixation, there is like a hook-like structure. So it's why it is designed like this is it has to fix inside the fibers of the heart. So that's why we have hook like structures at the tip. So once you keep the lead inside, it will be fixed like a hook, so it won't move anywhere, it will be fixed inside the muscular part. So this is a passive fixation. Next one is active fixation. So here what you have is you have a power source connected with it. So here you can see there is a spring like structure, right? If I zoom it, maybe you'll be able to see it clearly. So you're able to see a spring at the tip, right? So when there is an electrical pulse which is transmitted, this spring will attach it to the surface of the heart. Okay, so that is the active fixation. So it allows for lead positioning anywhere inside the heart chamber. So the lead can be placed anywhere. So this is the active fixation. So this lead can be moved inside the heart chambers and it can be fixed wherever it is needed. But this is a passive fixation. So once it is fixed inside the muscular framework, it won't move anywhere else. Okay. Next one is myocardial and epicardial leads. So these leads are applied directly to the heart. So these are the three different mechanisms. One is stab in, screw in, and suture on. So stab in is like a sharp like structure you can see here. So it's very sharp. So this will be directly kept inside. So another one is screw in. So you have a spring like screw like structure which can be kept inside the heart. Third one is suture in. So in suture in, you will be switcher on. So here you will be placing the lead and you will put a stitches around the heart. So this is also a permanently fixed. Okay, so these are the different fixation mechanism of the heart leads. Next one is cathode. So cathode is an electrode which is in contact with the heart tissue. So it's negatively charged and when the current is flowing, it will be a negative charge. Okay, so that is a cathode part. Next one is anode part. So anode is the part where the electrical impulse is received after the depolarization of the cardiac tissue. So it is positively charged when the electrical current is flowing. So it's basically like any electrical circuit you would have studied, right? So you have a negative uh, part and then you have a positive charge and then only then the circuit will be closed and the current will be flowing, right? So similarly you have an anode and cathode here. So anode will receive the electrical impulse and cathode will be negatively charged during the current flow. Next one is conduction pathway. So in between the anode and cathode, you have different tissues, right? So these tissues act as the conduction pathway. So the body fluids and the body tissues, the blood, the Purkinje fibers, all those things will act as a conduction pathway between your anode and the cathode. Okay, so during pacing, like I said, pacing is you are going to maintain the heart rhythm. That's what is called pacing, right? So what happens is the impulse will begin in the pulse generator. So instead of SA node, your pulse generator will generate the signal and then it flows through the lead and the cathode, stimulates the heart and then returns to the anode. So that's how the circuit will be. So if I'm going to draw this as a circuit, first it will start with the pulse generator, goes to the cathode, stimulates the heart and then returns back to the anode, positive charge, right? So that's how pacing is happening inside the pacemaker. So next one is types of pacemaker. This is just a simple classification. One is unipolar, another one is bipolar. So in unipolar, what happens is it contains a lead with only one electrode. Okay, so what happens is it flows through the tip of the cathode and then it returns through the body fluid to the anode. So this is a unipolar pacing system. Okay, in the figure you can see it very clearly. So it flows through the cathode tip and then returns through the body fluids to the anode. Okay, so that is the unipolar pacing system. Second one is bipolar pacing system. It has electrode, two electrodes within the heart. So you have anode and cathode placed nearby. So if you look at the previous figure, you can see the cathode is here and the closed circuit will act as the anode. But here you have anode and cathode specifically. So it flows through the electrode located at the tip and then stimulates the heart and then returns to the ring electrode above the lead tip. So this ring electrode is the anode. So you have two electrodes. That's why it's called a bipolar pacing system. Next one is unipolar and bipolar leads. So when you look at the tip of the leads, here in the picture it's not clear, but if you look at the actual lead, this is how it looks like. So unipolar lead will have a smaller diameter and it is usually exhibits larger pacing activates and the artifacts on the surface ECG. So when you are going to measure ECG using a unipolar pacemaker system, then you will have larger pacing artifacts because since it has only one electrode, you will have larger number of artifacts. So what is an artifact? Artifact is any unwanted signal, right? So when you measure any physiological parameters, whatever is not our interest, that is an artifact, right? Next one is bipolar lead. So here you can see the difference between the unipolar and the bipolar lead. So in unipolar lead, you just have only one circular coil. In bipolar lead, you have different layers. Like one electrode is inside and outside there is another ring electrode, right? So this is a bipolar lead. So here it is not sensitive to noise and it is much more accurate when compared to your unipolar leads. So the insulation used for the leads, it can be a silicone, it can be polyurethane or any other substance. So advantage is that when we use a silicone insulated lead, it is more inert, it is biocompatible, biostable, and it is repairable with adhesive and it is very reliable. So when you are going to place any component inside the body, the main thing which you should remember is biocompatibility, right? We have already studied that in medical instrumentation, no? So when we use leads which are insulated with silicone or any other biomaterial, then we have more biocompatibility. So polyurethane is again a biomaterial, so it has more biocompatibility, high tear strength, and it has a smaller lead diameter and low friction coefficient. So when we look at the history of pacemakers, it was first developed in the year 1960. So and it was an asynchronous pacemaker. So you know about the word synchronous and asynchronous, right? So synchronous is something which is having the same amplitude and frequency as that of the heart rhythm. If it is asynchronous, heart rhythm will be different, the pacemaker rhythm will be different. So that is what is an asynchronous pacemaker. So first when they invented the pacemaker, it was an asynchronous pacemaker because people just devised that instrument and they didn't know how to sync it with their heartbeat. So uh, there it has given, right? So pacing without regard to the heart's intrinsic action. So when we are discussing about the different types of pacemaker, you will understand this abbreviation better. So this VWO, DVI or the different types of pacemakers which we will be discussing in the next class. And then single chamber demand pacemakers were introduced in the 1960s. So and then in 1979, the first dual chamber pacemaker was introduced. So in dual chamber means it will be inserted in both atrium and ventricles. So the leads will be inserted in both chambers. And then the first single chamber rate responsive pacemaker was released in 1985. And today we use a lot of advanced pacemakers, like you have capsule size pacemakers that can be kept inside the heart, not very big pacemakers and all. So if you look at the picture, this was the earlier models which were used before. So the first upper left is the first implantable device, and then the second upper right, which is the great batch device, which was devised in the year 1960. and lower left is 1974 model made of titanium case. So previously people used to make titanium as a biomaterial, but nowadays titanium is not that much used. So if you look at the brand, it is made of Medtronics. Medtronics is like still the leading manufacturer of pacemakers, so they still do a lot of research in pacemakers, and they are like the leading manufacturer in the market. Next one is DDD device. So what is this abbreviation? We'll see it in the next class. That VVI, DDD, all these are like the different types we use, different types of pacemakers, and the abbreviations which we use in classification of pacemakers. So the middle one is the DDD device, and the last right one is the Kappa 400. Okay, so this is how the pacemakers, earlier pacemakers look like. But nowadays, if you look at the recent pacemakers, they are just in the size of a tablet, so it can be just kept inside, and it will do all the functionalities. So the battery size is also miniaturized. So here and all the battery size is somewhat bigger, but in recent devices the battery size is also small. And so that's it about pacemakers and its introduction. So let me just stop sharing my screen. Any doubts in today's discussion? Any questions?
மேம்
No? Yes?
மேம் இப்போ பேஸ் மேக்கர் நம்ம வைக்கும்போது அப்போ எஸ்ஐனோட அவங்க இன்ஆக்டிவ் பண்ற மாதிரி எதுவும் பண்ணுவாங்களா மேம்?
எஸ்ஐனோட inactive பண்ண மாட்டாங்க. It's very good question. Because what they do is, I said about synchronous and asynchronous, right? SA node வந்து full functioning ஆகாம இருக்காது. There will be a minor, என்ன சொல்றது, there will be a small electrical impulse which will be coming from the SA node. ஸோ அப்போ என்ன பண்ணுவாங்க அப்படின்னா, இந்த சின்க்ரனஸ் டைப் பேஸ்மேக்கரில் அந்த SA நோட்லேருந்து வர இம்பல்ஸ்க்கு தகுந்த மாதிரி இந்த பல்ஸ் ஜென்ரேட்டர்லேருந்து பல்ஸ் வந்து ப்ரொடியூஸ் ஆகும். ஸோ that's why it's called an synchronous type. ஸோ இன்னும் நம்ம டிஃப்ரெண்ட் டைப்ஸ் பார்க்கும்போது அதில் வந்து எந்த பார்ட் அஃபெக்ட் ஆயிருக்கோ அதுக்கு தகுந்த மாதிரி தான் அந்த சர்க்யூட்டை டிசைன் பண்ணுவாங்க. ஓகேயா? ஸோ அந்த சர்க்யூட்லேருந்து வர சிக்னல் வந்து இந்த ஹார்ட்டில் இருக்கிற சிக்னலோட மேட்ச் ஆகணும். அப்போ தான் வந்து ஹார்ட் வந்து பம்ப் ஆகும். Okay, so we can't completely ignore SA node or AV node or any other electrical activity. We have to keep the pacemaker circuit which will combine with the heart's electrical activity. ஓகே, ஸோ அப்படி தான் வந்து டிவைஸ் டிசைன் பண்ணும்போதே அப்படி தான் பண்ணுவாங்க. ஸோ அதை நான் இப்போ சொன்னேன், அந்த ஏசிரிப்ரஸ் டைப் ஃபர்ஸ்ட் இன்வென்ட் பண்ணதில் they totally ignored that heart's functionality. So they didn't actually think about all those things. So first time pacemaker design பண்ணும்போது they didn't think about all that. But then later, one by one, when they started with experimenting with the pacemakers, they tried to you know, implement all those things. Okay.
ஓகே மேம்.
Okay, any other question? No questions? Okay then I'll wind up this class today. So group activity என்னன்றது I'll post it in WhatsApp group. Okay?
Okay, ma'am.
Okay ma, you all can leave.
தேங்க்யூ மேம்.
Okay pa,
Thank
thank
you.
you.